Black holes are often described as the ultimate cosmic traps. Their gravity is so strong that once something crosses the event horizon, it can never escape. Not even light can get out. For decades, physicists believed that this meant black holes would simply exist forever. But today we think something far stranger is happening. According to modern physics, black holes slowly lose mass, shrink over time, and eventually disappear completely. To understand why, we need to combine two of the most successful theories ever created: Einstein's theory of gravity and quantum mechanics. Let's start with a simple question. What exactly is a black hole? A black hole forms when a massive star runs out of fuel and collapses under its own gravity. The collapse becomes so extreme that matter is compressed into an incredibly small region of space. Around this region lies a boundary called the event horizon. The event horizon is often described as the point of no return. If you cross it, every possible path through space-time leads deeper into the black hole. According to Einstein's theory of general relativity, this is where the story ends. Things fall in, nothing comes out. But quantum mechanics tells us that empty space is not actually empty. This is one of the strangest discoveries in modern physics. Even in a perfect vacuum, quantum fields are constantly fluctuating. Tiny particle-antiparticle pairs can briefly appear and disappear. These particles borrow energy from the vacuum for an incredibly short amount of time before annihilating each other again. Normally, this process happens everywhere in space without producing any lasting effect. But near the event horizon of a black hole, something unusual can occur. Imagine a particle pair appearing right at the edge of the event horizon. One particle falls into the black hole, the other escapes into space. Now the two particles can no longer meet and annihilate each other. To an outside observer, it appears as if the black hole has emitted a particle. This phenomenon is known as Hawking radiation, named after physicist Stephen Hawking, who first developed the theory in 1974. At first glance, this seems impossible. If a particle escapes, where does its energy come from? The answer is the black hole itself. The escaping particle carries energy away from the black hole, and according to Einstein's famous equation, energy and mass are equivalent. A useful way to write this relationship is E=mc². This means that when energy leaves the black hole, a tiny amount of mass must disappear as well. The black hole becomes slightly lighter. The effect is incredibly small. A stellar mass black hole emits an almost negligible amount of Hawking radiation. In fact, the cosmic microwave background radiation filling the universe is currently warmer than most black holes. This means that many black holes absorb more energy than they emit. However, as the universe continues to expand and cool over unimaginable timescales, Hawking radiation will eventually dominate. The black hole will begin to lose mass, and here is where things become even more interesting. The temperature of a black hole is inversely proportional to its mass. In simple terms, smaller black holes are hotter. As a black hole loses mass, its temperature rises. As its temperature rises, it emits more radiation. As it emits more radiation, it loses mass even faster. This creates a runaway process. Near the end of its life, the black hole evaporates more and more rapidly. The final moments could release an enormous burst of energy. How long does this process take? The answer is difficult to imagine. A black hole with roughly the mass of our sun would survive for about 10 to the 67 years. For comparison, the universe is only about 13.8 billion years old. The lifetime of such a black hole is so much larger that writing the number down requires dozens of digits. Supermassive black holes live even longer. Some could survive for around 10 to the 100th year or more. These timescales are so vast that every star in the universe will have died long before the last black holes disappear. Eventually, galaxies will go dark, stars will no longer form, the universe will become a cold and quiet place. And yet the black holes will remain, slowly shrinking, slowly radiating away their mass, until finally, after an almost unimaginable amount of time, they vanish. This idea remains one of the most fascinating predictions in modern physics. A black hole may be the closest thing nature has to a perfect prison, yet quantum mechanics suggests that even these cosmic giants are temporary. Given enough time, even black holes fade away, and that raises one of the biggest unanswered questions in physics. If a black hole eventually disappears, what happens to all the information that fell inside? Nobody knows for sure. And solving that mystery may require a completely new understanding of the universe itself.